That group 3, representing on cache memory. Someone is going to ask, what's a cache memory? Of course, a memory is a memory. So, a cache memory is not the computer primary memory nor permanent, but it's quite important for the computer performance. So, a cache memory is a small and fast temporary storage area located around the CPU or inside the CPU for efficient, easy, and near instant data retrieval. Here in this video, we're going to talk a lot about cache memory, but I'll hand over to my colleagues and they are going to talk about our objectives for today. Thank you.
Welcome, guys. In the previous chapter, we were able to get our appetite whet on the 7 course meal we'll be having throughout this journey. And we also we had a fair knowledge of what cache memory is, which we'll be building upon in this chapter. Without wasting much time, let's dive right into it. Before I start, I'd like to cite an example of a student who has been given an assignment to work on a research paper. There are two scenarios in this example. The first scenario being it that the student has the opportunity to go to the library, gather information, and come back and put it into the research paper he's working on. Or he has the opportunity to borrow all the books related to what he's working on and stores it next to his computer on his desk for faster access. In the second scenario, the desk has now become a cache memory, which is providing frequently asked data by the students faster to him. Now let's take a dive into the core of a cache memory. A cache memory is no different from a RAM, but has a significant difference, being it that the RAM is made up of a dynamic random access memory, which means it has transistors in it which have fluctuating currents running through it in order to store information. Cache memory, on the other hand, is made up of the static random access memory, which has capacitors in it which use static charges to store data. The cache memory is a non-volatile memory, but that doesn't mean it is the main memory. Let's build a concrete definition of what a cache memory is. A cache memory is basically a data storage which stores frequently as data for faster response time. That's basically what a cache memory is. Let's take some key characteristics of a cache memory. A cache memory is just an intermediary for faster data access. A cache memory also has one characteristics, being it that the more data being stored in it means the less time the CPU will have to go to the RAM to access information. In the next chapter, we'll be talking about the types of cache memory. But often you hear most people talking about cache memory relating to the CPU, either it's being on the CPU or around the CPU. This is because that's where the main action takes place. But in the next chapter, we shall know that cache memory is distributed all over across your computer, and we shall know exactly where they are distributed across. Thank you for making me be your waiter throughout this course. Hope to see you in the next course. Thank you very much. Welcome, guys, to this chapter of cache memory. In the previous chapter, we talked about what cache memory is and built our knowledge on what cache memory is. In this chapter, we are going to talk about the types of cache memory. And a key takeaway from the previous chapter, which we'll be using in this chapter, is what is cache. Cache is basically a storage which stores frequently asked data for those who ask for it. And another thing to also take note of is when you go online to search for the types of cache, you are often given the levels of cache, which at the end of this presentation, we'll get to know are two different things. So without any further talk, let's dive right into it. Types of cache memory. There are 4 types of cache memory: CPU cache, the disk cache, the browser cache, and the database cache. The CPU cache. In the process of the fetch, decode, and encode cycle, the CPU frequently communicates with the RAM for information to be processed. The RAM fails to give the CPU what it needs when it needs it. So cache memory is inculcated in this situation in order to give the CPU what it needs when it needs it. Now let's move on to the next one, disk cache. Disk cache, just like the way CPU communicates with the RAM also communicates with the hard disk. That's the main memory which stores the actual instructions of the program being run. The RAM also fails to get the information it needs when it needs it. So over here, cache memory is also inculcated in this place in order to ensure that the RAM gets what it needs when it needs it. Now let's move on to the third one. The third one is a bit interesting because we mostly hear of it but don't know what it is. Most of the times we are being told to delete our browser cache in order to get our devices running faster when we are trying to access a site. Browser cache actually works when you open your browser to access a site. So let's say if you are trying to access YouTube, what the browser cache does is that it downloads all the information about YouTube. That's being how the videos are arranged, how the search bar is, how to write down to how the next page is going to look like. So that whenever you press tap a video, automatically the next page comes up quickly, in order increasing your response time. So the cache memory over here ensures that your response time whenever you're accessing a website is very fast. But the interesting thing over here is that whenever a site is updated, the previous information of the site downloaded by the browser cache is not deleted. So meaning the new information is being added to the old one. And this keeps on happening. And the cache memory gets filled with previous outdated information of the site which you are accessing. So this tends to slow down the accessing response time of your browser when you are trying to access a website, because your browser cache is full, thereby cannot download information of the current sites you are on in order to give you faster response time to the next page or whatever button you click. That's why we are being asked to delete our browser cache whenever our browsers begin to slow down. They don't give us the kind of efficiency we need. Let's move on to the last one. The last one is the database cache. The database cache, as we all know, is database stores huge amounts of information. And in this time, it's not a communication between two electronic components. This time it's a communication between a human being and an electronic component, because I'm the human being asking for a data from an electronic component. And the cache memory in this situation helps me get what I want faster, because there are thousands of data being stored in the database. So the cache memory stores what I frequently ask for from the database in order to get what I want when I need it. Thank you guys for being with me to the end of this chapter. Hope you enjoy the rest of the chapters, and I hope at the end of the whole presentation, you will build your knowledge on what cache memory is, how cache memory works, and also start to appreciate the kind of magnificent work your PCs, your devices have been doing in order to give you an enjoyable experience with your machines. Thank you.
Okay, so my name is Excel Crab. I'm continuing from where my colleagues left. The main idea of cache memory is cache memory temporarily stores information, data, and programs that are usually used by the CPU. I'm here to take you through how the cache memory works. So when data is required, the CPU automatically turns to the cache memory in search of faster data access. This is because the RAM is slower and farther away from the CPU. Cache memory reduces latency and increases performance by minimizing the need to access the main memory multiple times for the same piece of instruction set. So one may ask, what does the cache memory consist of? The cache memory consists of the tag, data, and valid bit. When we talk about the tag tells us what address data we want comes from, and data. The data is the actual information from the memory that we want to access quickly. So now let's talk about valid bits. As the name depicts, validity. Valid bit tells us if the cache is garbage or good. So in summary of how the cache memory works, we can see that the cache memory works as a high-speed primary storage memory, which is essential for multitasking in a computer system. The cache memory only loses its power when there is switch in programs or when the computer system goes to sleep. In our subsequent videos, you will understand the impact of cache memory on the computer system. Thank you.
My name is Masa Ansumi. I'm in Group 3, Computer Architecture. So I'm going to continue from where my friend stopped, and that will be the level of cache memory. Cache memory exists at 3 levels, with each level getting progressively larger but slower than the one before it. That's L1, L2, and L3. So the L1 cache is typically placed into the processor itself and stores recently used instructions or data that are most likely to be required again. So this makes it extremely fast as compared to other type of storage. But however, it is small. The level 2 and then level 3 caches are typically external components that store additional information that may be needed by the processor in order to run efficiently. They are slightly slower than level 1 but still provides quick access when necessary.
Okay, so my name is Kingsley and I'll be taking over from where my classmates left off. In this part, we'll be talking about the impact of cache memory on our system performance. So, the use of cache memory helps to reduce the latencies by minimizing the amount of time needed to access data stored in the main memory. By reducing latencies, system can perform more operations per unit time, which translates into improved system performance. Cache is the fastest and the smallest component of a memory in a computer system. A cache's primary purpose is to increase data retrieval by reducing the time needed to access the underlying slower storage layer. The cache speeds up access to data in applications. Because of their size, they impact largely on overall system performance due to their speed and efficiency. So we're talking about the advantages of cache memory. 1. The cache memory is faster than the main memory. 2. It consumes less access power as compared to the main memory. 3. It stores a program that can be executed within a short period of time. 4. Data can be accessed for temporary use. So my conclusion is that cache plays a major role in enhancing system performance by reducing data access time, increasing CPU efficiency, and improving energy consumption. However, the benefits of cache memory are maximized only when it is properly sized and managed. Thank you very much for watching this part.
I am Lawrence at the Federal Dem, and I'll pick up from where my colleagues stopped. I'll be taking us through the effect of the hits ratio on the average access time. So before we go into that, I would want us to understand the concept when we say cache hits and cache miss. I want us to understand the concept of what we mean by that. So when we say cache hits, what do we mean by cache hits? So cache hits occurs when we request a piece of data and then we find it in the cache. So this means that the data we requested for is already stored in the cache. And this makes the retrieval of that data very fast. So when the data is already stored in the cache, we wouldn't have to go back to the main source, the original source, before we get that data. And it's the same thing with cache miss. Cache miss is actually the opposite of cache hit. So cache miss occurs when we request a piece of data and we don't find it in the cache. So then we would have to go to the main source, the original source, to retrieve that data. And the same thing here, because the data is not stored in the cache, so it makes the retrieval a bit slower, slightly slower than the cache hits, because for cache hits, the data is already stored in the cache, so retrieving it is super fast. Let me give a scenario to paint a clearer picture on this. So I'll use my lecturer in my class rep, for example. Okay, so let's assume I miss lectures. So my class rep is acting as the cache here, and my lecturer is the original source, the main memory. Okay, so I miss lectures and I go to class the next day and an assignment was given. Because I wasn't in class, I don't have the assignment. So I go to class the next day and I go to my class rep. Oh, class rep, I missed lectures and an assignment was given. Can I please have it? So I could also do and submit. So when my class rep gives the assignments to me, that is a cache hit because my class rep is acting as the cache. Okay, and I request a piece of data and I got it from him. So that is a cache hit. But then if I ask my class rep for the assignment and he doesn't have it, then I would have to go to the original source where the assignment is coming from, which is my lecturer. So my lecturer is now the original source.
So if I don't get the data I want in the cache, then I would have to go to the main memory, the original source, to get that data. That is where cache miss occurs. So my lecturer is the original source, my class rep is the cache. So I request an assignment and I don't get it from my class rep, and I would have to go to my lecturer for that assignment. That is a cache miss. But when I request for the assignment and I get it right there from my class rep, that is a cache hit. And of course, I wouldn't miss lectures and I'll go to my lecture to take an assignment, because offense number one, I missed his class. So there's no way I can go to my lecturer and ask him or her for an assignment that him or her gave when I wasn't in class. So yeah, so that is the whole concept when we see cache hits and cache miss. So now let's look at the effects the hit ratio has on the average access time. So the hit ratio, which is the fraction of all memory accesses that result in a cache hit, significantly impacts the average access time of a system. The average access time can be calculated using the following formula. So average access time equals hit ratio times cache access time plus miss ratio times miss penalty. So we are hearing hit ratio, cache access time, miss ratio, miss penalty. What exactly do we mean by those? So when we say hit ratio, it is the percentage of memory accesses that result in a cache hit. Okay, so when we say hit ratio, it means the percentage of memory accesses that result in a cache hit. Then we look at cache access time. Cache access time, this is the time it takes to access data from the cache. So the cache hit. So when we request a piece of data, the amount of time it takes for us to access data, that particular data we are requesting from the cache, that is what we call the cache access time. Then the miss ratio. So the miss ratio is the percentage of memory access that results in a cache miss. So we could say, okay, that is it. The percentage of memory access that results in a cache miss. So into bracket, miss ratio equals 1 minus hit ratio. Okay. So when we say miss penalty, what is the miss penalty? So miss penalty is the additional time required to fetch data from the main memory or the lower level storage when a cache miss occurs. So when we say the additional time required, so let me use the same scenario. I go to my class rep, I request for the assignment, I don't get it. Then meaning I would have to spend another time, because I can't just get up and go and meet my lecturer. First, I would have to either call or text him or go to his office. And when I go there, I would have to wait for a bit of time. And I would have to explain myself why I didn't come to his lectures. You see, this is just a scenario I'm putting. So all the time. So if I had gotten the assignment from my class rep, that would save time. But I didn't get it there. So I would have to go to my lecture. So that is additional time. You get it. So that is additional time. So when we see the miss penalty, that is the additional time that is required to fetch data from the main memory or the lower level storage when cache miss occurs. So when we say high hit ratio and low hit ratio, what do we mean by those? So if the hit ratio is high, most memory accesses are resolved quickly from the cache. This leads to a lower average access time, enhancing the system's performance. Talking about system performance enhanced, one benefit of cache hits, one benefit of cache hits is that when you request for a data and you get it right away, because the data is stored in the cache memory, it makes the overall performance very fast. Okay, because it saves time. So it enhances the overall responsiveness of the application, and it enhances the overall system performance. Okay, because you request something and within a twinkle of an eye, you get your thing. But here lies the case: you request something and then you have to wait a bit more. You have to wait a little more to get what you requested for. That will enhance the system's performance. I don't know if I'm making sense here, but yeah, that's just by the way. So let's look at the low hit ratio. If the hit ratio is low, a larger proportion of memory accesses results in cache misses. This increases the average access time since accessing data from the main memory takes longer. And I could compare this to the same scenario. If I'm going to request an assignment from my lecture, as I said earlier, one, I would have to explain why I wasn't in class, and that would take much longer to get my assignment. But with my class rep, maybe class rep, oh, oh, Charlie, I know from class, so this, and that, like body. But when I go to my lecture, I would have to explain, and my lecturer can say I should write a letter to explain why I wasn't in class. So me getting that assignment, even if I get assignment, I would have to do extra tasks to sum up to me not coming to class. So that is just by the way. So the low heat ratio, if the heat ratio is low, a larger proportion of the memory accesses result in cache misses. This increases the average access time since accessing data from the main memory takes longer. Okay. So let's consider this example. So we have cache access time, which is 1 nanosecond, represented by NS in the bracket. Then we have miss penalty, 100 nanosecond. Then we have the heat ratio, which is 90% into bracket 0.90. So using this formula, average access time equals 0.90 multiplied by 1 nanosecond, all into bracket, plus 0.10 multiplied by 100 nanosecond, all into bracket. So the average access time equals 0.9 nanosecond plus 10 nanoseconds. Someone will ask, how did we get a 0.9 nanoseconds, which we are adding to the 10 nanoseconds? And how did we get a 10 nanoseconds? So when we multiply 0.90 by 1 nanosecond, when we multiply 0.90 by 1 itself, we are getting 0.9. And when we multiply 0.10 times 100, we are getting 10. So that's how come we got the 10 nanoseconds that we are adding to the 0.9 nanosecond. Then when we add 0.9 nanoseconds to 10 nanoseconds, we get 10.9 nanoseconds. I think the formula explains itself. So easy to understand. But let's assume the heat ratio drops by 50%. Okay, into bracket 0.50. Average access time equals 0.50. So now we are multiplying the heat ratio. We are multiplying the heat ratio, okay, by the cache access time. Okay, so 0.50 plus 1 nanosecond plus 0.50 times 100 nanosecond. So same scenario here, when we multiply 0.50 by 1, we'll get 0.5, and we multiply 0.50 by 100, we are getting 50. So that's how come we have 0.5 nanosecond, which we are adding to 50 nanosecond. And when we add 0.5 nanosecond to 50 nanoseconds, we'll get 50.5. So that's 50.5 nanosecond. And same issue here, the formula explains itself. So easy to understand. So these examples are to illustrate how a decrease in the heat ratio can significantly increase the average access time, thereby reducing the system's overall performance. Therefore, optimizing the heat ratio is crucial for efficient system performance. So I'll close the docket on this chapter, and I'll hand over to my next colleague who will take us through the benefits of cache memory. Thank you.
Hi, I'm Jojo. To add to what my group member said, let's look at the benefits of cache memory. Okay, so cache memory offers improved latency, increased throughput, reduced power consumption, and greater scalability. It is particularly well suited for latency-sensitive applications like web browsing. Fast forward. Okay, so cache memory conserves battery life in mobile devices and extends device longevity by minimizing the need for power data access from slower storage. Finally, cache memory scalability allows it to adapt a system's changing needs without requiring upgrade or replacement. The stated point discussed by my colleagues and I. We hope this point best explains what a cache memory is and how it works.